Hello students, welcome to the lecture on sets, and after this lecture we will be able to learn the following objectives. Talk about the basic concepts of set theory, give details of the operations on sets, talk about the partition of sets, give details of the Cartesian product of sets, describe Venn diagrams. Let us start with the introduction of sets. The concept of set is fundamental to mathematics and computer science. Everything mathematical starts with sets. For example, relationships between two objects are represented as a set of ordered pairs of objects. The concept of ordered pair is defined using sets. Natural numbers, which are the basis of other numbers, are also defined using sets. The concept of function, being a special type of relation, is based on sets, and graphs and digraphs consisting of lines and points are described as an ordered pair of sets. Though the concept of set is fundamental to mathematics, it is not defined rigorously here. Instead, we rely on everyone's notion of set as a collection of objects or a container of objects. In that sense, set is an undefined concept. It is also assumed that sets have certain obvious properties usually associated with a collection of objects, such as the union of sets exists. For any pair of sets, there is a set that combines them, etc.
I'm Professor von Schmohawk, and welcome to YU. This series of lectures is about algebra. In these lectures, we will explore the concepts which are fundamental to algebra. One of the most fundamental concepts in algebra is the concept of a set. A set is simply a collection of objects called elements. The elements of a set can be anything: numbers, people, letters of the alphabet, other sets, and so on. Sets are often denoted with capital letters. Certain important sets are designated with special symbols. For example, the empty set, which is a set with no members, is designated with a /O. Remember that /O does not represent the number 0. It denotes the set which contains no elements. Other important sets are sets of the various number types which we explored in pre-algebra. The set of natural numbers is typically designated by the bold-faced letter N. Likewise, the set of integers is designated with the letter Z, the set of rational numbers is designated by Q, and the set of real numbers is designated by R. Another important set is the set of complex numbers C, which we will discuss in a lecture later in this series. We can indicate that an element is a member of a set by using the symbol for set membership. For instance, we can say that the element 1 is a member of the set of natural numbers. We can also indicate that an element is not a member by using the negation of this symbol. For example, we could state that 1/2 is not a member of the set of natural numbers. We define a set by specifying all its members. There are several ways to do this. One way is by writing a list of all the members of the set, separated by commas, and enclosing the list in curly brackets. For instance, we can define set A to be a set whose members are the numbers 1, 2, and 3. Or we can define set B to be the set whose members are the colors red, white, and blue. An important rule to remember when listing the members of a set is that each element must be unique. No two members of a set may be the same. For sets with lots of members, if the list of elements continues in some obvious way, an ellipsis can be used to indicate a continuation of the pattern. For example, the set of integers between 3 and 100 could be written like this. This can be very useful when specifying the membership of infinite sets. For instance, the set of natural numbers can be written with an ellipsis following the first few numbers to indicate that the list continues forever. Likewise, the set of integers can be written with an ellipsis on either side to indicate that the numbers go on forever in both the positive and negative directions. Fewer or more elements can be listed as long as the pattern is clear. Instead of listing each member, a set can also be defined by stating the properties that its members must satisfy. For example, for set A, instead of listing the elements, we could say that A is the set of natural numbers less than 4. And we could define set B as the set of colors of the American flag. Another option is to enclose the description in curly brackets. The brackets are read as the set of all. For example, A is the set of all natural numbers less than 4. There is also a more rigorous mathematical notation for describing a set called set builder notation. To define a set using set builder notation, we choose a symbol, typically a small letter, to represent any element of the set. For example, let's use the letter X to represent a typical element of set A. Now, in the brackets we write X followed by a vertical bar, and then state the properties that every element X must satisfy. In this case, every element must be a natural number and less than 4. The vertical bar means such that. So we would read this definition as A is the set of all elements X such that X is a natural number and is less than 4. You may sometimes see a colon used instead of a vertical bar. So far, we have seen how to define sets and their members through the use of set notation. In the next lecture, we will learn about various types of relations between sets.
Basic concepts of set theory. The word set in mathematics was first of all used by George Cantor. According to him, a set is any collection into a whole of definite and distinct objects of our intuition or thought. However, Cantor's definition faced controversies due to the forms like definite and collection into a whole. Later on, a single word, distinguishable, used to make the definition acceptably. A set is any collection of distinct and distinguishable objects around us. By the form distinct, we mean that no object is repeated, and some lack the term distinguishable, we mean that whether that object is in our collection or not. The objects belonging to a set are called as elements or members of that set.
What is a set? A set is a collection of objects, and the objects themselves are called elements of the set. Okay. So, for example, you can have the set of natural numbers n, and you can think about a set of books, or you can think about the set of even non-negative integers less than 10, which is denoted by this. Usually, a set is denoted like this, and the elements are denoted like this. It is written within flower brackets. All the elements are written within flower brackets. So, S denotes a set which consists of elements A, B, C, D. Now, you say that A belongs to S. You use this symbol for belonging to. So, this means A belongs to S, or A is in S. In contrast to that, if you write say some E does not belong to S, it is not here. So, E does not belong to S, or E is not in S. Now, you can also have a definition like this. For example, the set of even numbers, even non-negative integers, we can say that E is equal to x, where x belongs to n, it is a non-negative integer, and there is a y belonging to n such that x is equal to 2y. This denotes the set of all even non-negative integers. Now, you are using a predicate, to define E. Such a definition is known as implicit definition, whereas a definition of this form is known as explicit definition. So, a set can be defined using explicit definition or implicit.
Two forms of representation of a set: set builder form representation of set and tabular form or roster form representation of set. In set builder form of representation of set, we write between the braces a variable x which stands for each of the elements of the set. Then we state the properties possessed by x. We denote this property by px and separate x and px by a symbol, or read as such that a is equal to x is to px. A is equal to x is to x is capital of states, or a is equal to x is to x is a natural number and 2 less than x less than 11. In tabular form or roster form, the elements of set are listed one by one within braces and one separated by each other by commas. B is equal to Lucknow, Patna, Bhopal, Itanagar, Shillong, or B is equal to 3, 4, 5, 6, 7, 8, 9, 10.
Now let's write here these following listing methods sets, or you can say rosters form of sets into the set builder form. Alright, and the first one is here 3, 6, 9 and 12, and we need to write in the set builder form. So don't you think this 3, 6, 9 and 12 are something like this, like 3 times 1 and then 3 times 2 and then 3 times 3 and then 3 times 4? It is something like this, right? So it's here, what you're looking here, it's something like 3 times n, and where n is actually 1, 2, 3 and 4. So how you can represent that? So the first one, you can say that let me suppose this is set A, and set A is equal with x such that x equals to 3n, and n belongs from natural number, and n is greater than or equals to 1 but less than or equals to 4. Alright, so see, this is the way how to represent a given set into the set builder form. See here, x such that x equals to 3n, it's n. Alright, it's n, 3n, and here n is from the natural number, n belongs from natural number, and n is equal with is greater than 1, means greater than or equals to 1 means you need to include 1 also, and is less than or equals to 4. So less than 4 and greater than 1, all the natural number, that is 2 and 3. So 1, 2, 3, 4. If you put here, you'll get 3 times 1 time you'll get 3, and then you'll get 3 times 2, you'll get 6, and then 3 times 3 you'll get 9, and 3 times 4 you get 12. Alright, this was the first one. So the second one, our second roster form set is 2, 4, 8, 16 and 32. Right, so here first you should know the trick, how we can represent them as in the form of x or in the form of n. How? First, that you need to think. So here I'm looking, it's like 2 for 2 square, which is 2 cube. Yeah, we got it. So it is like 2 to the power 1, 2 to the power 2, 2 to the power 3, right, 2 to the power 4, 2 to the power 5. Now see, 2 to the power 1, 2 square, 2 cube, 2 to the power 4, and 2 to the power 5, that's 32. So can't I say like it is 2 to the power n, and where my n is 1, 2, 3 and the 4 and then 5, alright, till 5. So how I'll represent, suppose this is my set B, so my set B is equals to x such that x is equal with 2 to the power n, and n belongs from natural number, and you can say that n is greater than or equals to 1 but less than or equals to 5. Alright, that's it. So n is from 1 to 5, it means n equals to 1 2 3 4 5, and x is actually 2 to the power n. So first time I'll write 1, then I will get this one. When I'll get 2, when I'll put n as a 2, then you'll get like 4, and I'll get, when I'll put n as a 3, then I'll get 8, and 4 as 16, and 5 as 32, like this. That's it. And the third one is, here I have 5 25 125 625, right? It's 5 25 125 and 625. So it's again quite easy. It's in the base of 5. It is actually, all right. Like 5 to the power 1, 5 to the power 2, 5 to the power 3, 5 to the power 4. So you can exactly write in the same way, and where you can do like here in the same way, you can say the C, right, and x, so that x equals to 5 to the power n, where n is from natural number, and it is equals to n greater than n, but it is up to 4. It's up to 4, right? So equals to 4. That's it. It's the same. It both are same. All right. I don't know why the similar questions I give here. Sorry. Well, here is 2 4 6. All right. Another one is, fourth one is 2 4 6 and dash 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 dash. Yes. What does this dash 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 means? Yeah, I have told you there, that's infinite set. So there are huge number you cannot count. It's unlimited numbers of even numbers are there. It's 2 4 6, and then next will be 8, and then 10. These all are even numbers, right? And we represent even numbers like 2n, and n are all natural numbers. N belongs from all natural numbers. So you put either 1 or 2 or 3 or 4 or 5, anything you put, you'll get always an even number. If I'm putting 1, I'll get 2 times 1 equals to 2. If I'm putting 2, then I'll get 2 times 2, I'll get 4. So all the even numbers I'm going to get. So how I will write it here now? If you want to write in the very simplest way, you just write like, suppose this is D, where an x, so that x is even natural number. Even is even natural number. That's it. And if you want to write something even more better way, then you can write like x, so that x equals to 2n, and n belongs from natural number. That's it. And natural number are infinite, you know, so that's why you can also put here infinite times, and you'll get infinite numbers. That is dash dash dash, and always you'll get an even number. All right, that's it. And the last one is 1 4 9 and 100. This is a little bit good. Suppose this is E. Let me suppose this is E. 1 4 9. Already I know it hit on your brain what we have to do, but again I'm doing it. It is like this, right? 1 square, and then 2 square, and then 3 square, and dash 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 till 10 square. What does it mean? Like it's something like n square, right? It's n square, but n is 1 2 3 till 10. Alright, so how we can represent this? We can represent simply like E is a set in which x means its members, such that x is equal with n square, and n belongs from natural number, and n is greater than or equals to 1 but less than or equals to 10, including 10 and including 1. That's why I write here. Let's do now a little bit problem related to the representation of the set. And here question is saying we have to represent these all sets into the form of roster form, or you can say listing method or tabular form. Those all are same. Alright, so let's go one by one. So first one I'm writing A, right? It contains the member x, such that x is an integer and x is greater than -3 but less than 7. Alright, greater than -3 but less than 7, and x is integer. So you're perfect in those all things dealing, right? So it's integer, so it will be first. Integers means like 1 2 3 4, or you can say -1 -2 -3 including the 0. Alright, so it is -2 -1 0 1 2 3 4 5 and then 6. I'm not going to write 7 because it's less than 7. Alright, similarly I had not included here -3 because x was greater than -3, and that's it. So second one, B, X says that X is the natural number less than 6. So natural number less than 6. So B, suppose natural number, like see, there is no problem of order, so you can start from the 5 also, and then you can write 4, then you can write 3, right? But you know also why to go from the back. You can easily start from the first one, because the first natural number is 1, and then 2, and then 3, and then 4, and then 5. You're not going to write the 6 because your natural number is less than 6 now in the given set B. Alright, so that's it. And the third one is here, X such that X is the 2-digit natural number such that the sum of its digit is 8. Okay, we need to write 2-digit numbers like 44 with sum, 4 and 4 if you add, like 4 and 4 if you add, you'll get 8. So this kinds of the numbers, there are a lot of 2-digit numbers that we have to write in the set C. Okay, yeah, that was quite interesting. I like this set C. So first one, as I said, 44. Alright, because 4 and 4 if you add, you'll get 8. Similarly, you can write 26, 2 plus 6, 8. Alright, so you can reverse it also, 62. And similarly 33 and 5, 35. So you can write 53 also. And 71, because 7 and 1 is 8. So you can write 17 also. And 8 itself, so 80, and you cannot write here 08. You cannot write 08 because 08, it's actually 1-digit number, just 8 is there, so you have to remove this. So I think these are only the total number of elements: 44, 26, 62, 35, 53, 71, 17. Okay, I think it is. Alright, if I missed something, then please comment just below this video. I'll try to add later. So the fourth one, yeah, the D. X is a prime number which are divisor of 60. So all the prime number which can divide the 60. Alright, so D is such a set which is including all the numbers which can divide the 60, not the numbers, only the prime numbers. So 60 can be divided by 2. Alright, we're not going to include 1 because 1 can also divide, because they are asking prime numbers. So 2 is the first prime number that can divide 60. Another one is 3 times 20. Alright, another is 4, but I'm not going to write 4 because 4 is not my prime number. And 5 times 12. Alright, so next one is 6, but I don't have to write the 6 here. And then 7, no, another one anymore, no. 15, not. So these are 2, 3 and 5. These are only the prime numbers which can divide 60. Alright, to confirm, you can do the prime factorization of this. So it is 2 times 30, and again you can say 3 times 10, and again you say 2 times 5. So what are those? Finally you got 2, you got 3, and you got 5. So 2, 3 and 5 are only the prime divisor, right? Prime factors of the 60. Prime divisor or factors are the same, right? So X is a prime number which is divisor of 60. So you got the set what you want. And now let's go for the fifth one. And our fifth set is E is the set of the all letters in the word trigonometry. Wow, very nice. Okay, so set E, and I have told you already the rules. No duplication with no tension of order. Alright, so first T is the member, and then R, alright, then I, and then G, then O, then N, then again O is there, but duplication we don't do, right? We don't repeat it, so we can cancel it. Then M, then E I haven't written till, I can write, and then T again comes, right? But T I have already mentioned here, so there is no need to write this T. You can cancel this, you can avoid this, alright? And then R is also already mentioned here, so I'm not gonna write that. And then Y. I've given you the rules that no duplication with no tension of order. So this is my set, alright? My set, S-E-T. Might be making wrong pronunciation, I'm sorry. Set, alright? So the sixth one. Now F, the set of all letters in word better. Again, so F is another set which includes B, alright? So first write B, and then E, and then T. T is repeating again, so I'll cancel this. One more time, E is repeating, I'll cancel this, and R, right? So this is the set of better. We don't repeat the words while writing the set. I've already mentioned this is the way of representing.
Hi, let us look at the concept of different types of set. Now the first one is a singleton set, and a singleton set simply means that it has only one element or a single element. A quick two examples, let us say that we have a set A which has only one element, which is 0. Now this is an example of a singleton set. Another example is the set B, which has one element, which is 2, which is the only even prime number, and therefore this is a singleton set. Let us understand what do we mean by an empty set. Now empty set gives you the notion of 0 in sets. We have a notion of 0 in numbers, which implies that there is nothing, and that similar idea of nothing in set leads to the definition of an empty set. And what an empty set is? It is a set which has no elements. There is nothing, no element within that set. And mathematically, in set theory, it is denoted by either having two curly braces without writing any element in between, or you use the symbol which is known as phi. Now these two are the common representations of an empty set. Let us look at a couple of examples. Let us say that we have a set A which comprises of all elements x such that x is greater than 1 but x is greater than 2, and the condition is that x is a natural number. Now let us write down the natural numbers. We know that the natural numbers start from 1, 2, 3 and so on. Now the very definition of natural numbers implies that there is nothing between 1 and 2 or 2 and 3. Therefore, it is impossible to have any natural number between 1 and 2, and therefore the set A is a null set, or you can also write it as a phi. It is an example of an empty set. Let's look at another example. We say that B is a set comprising of x where x is an even prime number greater than 2. Now let us write down the prime numbers. So the prime numbers start from 1, 2, 3, 5, 7 and so on. Now do we see any even prime number that is greater than 2? Now 2 is the only even prime number. Rest all these prime numbers are odd. Therefore the set B is a null set. B is a null set. You can just write it as phi. It consists of no element because there cannot be any even prime number greater than 2. So in this video we discussed about a singleton set and a empty set. We'll see you in the next session. Hi, let us continue our discussion on the different types of sets. In this video we will discuss what are finite sets and infinite set. Now as the name implies, finite sets are sets that have countable elements, or in other words they have a definite number of elements, which simply means that you can count them. It is not a very huge number and you can put a definite number to the elements in the set. Let us understand using example. Let us say that we have a set W which is set of days in a week. Now we know that there are 7 days in a week, and therefore the set W is a finite set. Let us look at another set. Set S is a solution of equation this x square minus 16 is equal to 0. Now let us look at what will be the solution to this equation. So we say x square minus 16 equals 0. Transposing the 16 towards the right hand side, we get a positive 16, and if we take the square root of both of the sides, we get x equals plus or minus 4. Therefore the set S consists of the elements, the set S consists of the elements plus 4 and minus 4, and therefore it is a finite set. 2 elements. Let us look at what do we mean by infinite sets. Now it is straightforward. Infinite set simply means uncountable elements. The number is so huge we just cannot put a number to it. Uncountable, or you can also say as indefinite elements, which means that you just cannot put a definite number to the elements in that set. Let us look at some examples. Let us say that we have a set P which consists of set of points on a line. Now if you recollect, a line is defined as extending in both the directions. Let us say that this line is L, and how many points can you have on a line? Because it is extending in both the directions, you can just keep on having so many points. It's just difficult to put a number, and therefore that's where we say, oh well, a line has infinite points. Infinite points. Therefore, the set P, which has a set of points on a line, is an example of an infinite set. So this was the discussion on finite and infinite set. In the next video, we'll continue our discussion further and learn some more type of sets.
Students, and they may have this note-taking sheet, but I will try to make it a useful video for other people on YouTube. First of all, for our definitions, the union of two sets A and B is a set of all elements in A or in B or possibly in both, and we use the U shape for to indicate union. Intersection of two sets is a set of all elements belonging to both A and B, and we use this symbol for intersection. Complement of a set A is a set consisting of the elements of the universal set which are not in A, and the notation that we use is A with a bar over it. And I'll do set subtraction here a little bit later. So let's go ahead and go over to the Venn diagram applet. Let me go ahead and show you how this works. I can click in these regions and shade them if I want to. If I'd like to shade with a different type of shading, I can do it this way. I can clear here. I can shade an entire set A, which is this entire set. I can shade an entire set B by hitting this one, and an entire set C like this. Well, let's go ahead and do number one, which is A union B. Well, A union B, I'm going to need everything in A. I'm going to need everything in B. All these points are either in A or in B or both. And then I hit check. Oops. Let's try that again. Let's hit check. And it says very good. Now let's go to the next problem, which is intersection. Now I'm going to do a little bit of scratch work, so to speak, here. I'm going to take set B, and then I'm going to change my hash marks to diagonal, and I'm going to have set C. And now we need to have the points that are in set B and in set C at the same time. That's these points right here. So this is the region that I want for my answer. So I'm going to go ahead and clear, and I'm going to just shade these regions for the problem B intersect C. And I'll hit check, and that's very good. In my next example, I'd like to do A complement, and I have written that right over here. A complement is A with a bar over it. Means everything in the universal set outside of A. So I'm going to go ahead and shade that. I need this region on the outside here, but I also need this region, and this region. Notice that A is not shaded, but everything outside of A is shaded. This is A complement. The next example I'd like to do is A intersect B in parentheses, and then the complement of that. So we need to do the work inside the parentheses and then take the complement of it. A intersect B is going to be the points that are in both A and set B at the same time. It's this overlap. And now we want the complement of that. In other words, everything outside of this shape. So on this applet, you cannot erase. So I'm going to start over. And I'm going to shade everything outside of, I'm shading everything outside of A intersect B. This is the complement of the quantity A intersect B. Let's check it. And that's correct. The last example I'd like to do is set subtraction. B take away C. This is all the elements in B which are not in C. So I start with set B, then I remove the points that are in C. Now I have shaded B minus C. Have a great day.
A set partition S of a set is a partition of set into subsets called parts and represented as a set of sets. By extension, a set partition of a non-negative integer n is the set partition of the integers from 1 to n. The number of set partitions of n is called the nth Bell number. There is a natural integer partition associated with the set partition, that is the non-decreasing sequence of sizes of all its parts. There is a classical lattice associated with all set partitions of n. The infimum of two set partitions is the set partition obtained by intersecting all the parts of both set partitions. The supremum is obtained by transitive closure of the relation I related to J if they are in the same part in at least one of the set partitions. Given any set of distinct objects, how many ways can it be split into subsets? Such a division is called a set partition. More formally, a set partition of a set of distinct objects S is a set of disjoint subsets whose unit is S. Cartesian product. Let's watch this video for clarification or Cartesian product.
In this video, we shall learn one of the very important topics of theory of relations, and this topic is Cartesian product of two sets. We can define the Cartesian product of two sets as follows. Let A and B be any two non-empty sets, then the set of all ordered pairs AB such that A belongs to capital A, B belongs to capital B is called Cartesian product of two sets A and B. It is denoted by A cross B and read as A cross B, such that then we can write it as A cross B is the set of all ordered pairs where A belongs to capital A and B belongs to capital B. And if set A is an empty set or B is an empty set, then A cross B is also an empty set. Let me give you some examples to make you understand in a proper way. Suppose we have A equals to 1 and 2 and B equals to 3 and 4, and then we have to find if A equals to B and A equals to the set of 1, 2 and B equals to the set of 3 and 4, then find A cross B. Suppose this is the question. Then how can we solve it? Let us see. We are given A equals to set of 1, 2 and B equals to 3 and 4. Therefore, A cross B will be equals to, we shall make pair of 1 with 3 and 4 like this, 1 with 3, 1 with 4. And now we shall make pair of 2 with 3 and 4, then it will be 2, 3 and 2, 4. So this is A cross B. And we can also find B cross A like this. First of all, we shall make pair of 3 with 1 and 2. So we shall write 3, 1 and 3, 2. And now we shall make pair of 4 with 1 and 2. Then it will be 4, 1 and 4, 2. So this is B cross A. And it is important here that A cross B is not equals to B cross A. This is very important.
Venn diagrams. A Venn diagram is a visual representation of any given set. In Venn diagram, the rectangle box indicates universal set U, and we can show other sets by making small circles in that rectangle box. If we have two sets A and B, then we can draw a Venn diagram for operations which we can operate on sets. Summary. Now in the end, let us summarize what we have learnt in this lecture. A set is any collection into a whole of definite and distinct objects of our intuition or thought. A set is represented by using all its elements between braces and by separating those from each other by commas. A set partition of a non-negative integer n is the set partition of the integers from 1 to n. Cartesian product of set A and B is not equal to Cartesian product of set B and A. A set having infinite number of elements, that is a set where counting of element is impossible, is called as infinite set.